Welcome back to video 4 of the differential equations, or this is video 4 of this day, sections 4.1 and 4.2. And we want to start by recalling linear independence and linear dependence. So if a sequence of functions yi are linearly dependent, that means that some constant times the first function, and let's talk about just two functions in this case, plus some constant times y2 is equal to 0. There exists some non-zero constants c1 and c2 such that the linear combination of y1 and y2 with c1 and c2 are equal to 0. This means that we could write say y1 as negative c2 y2 over c1, also known perhaps as just some new constant times y2. So if y sub I then are not linearly dependent, that is, are linearly independent, then this first supposition is not true. That is, c1 y1 plus c2 y2 is not equal to 0, which means the direct consequence of that y1 is not equal to some constant times y2. Or equivalently, y1 divided by y2 is not equal to some constant. Well, these are still just functions of x. So if y1 and y2 are not constant, that must mean that if y1 and y2 are linearly independent, this quotient y1 divided by y2 must be equal to some different function of x. Again, it can't be constant, so it must be some function of x. Or equivalently, y1 is equal to some function u times y2. So again, this is a consequence of linear independence. So let's see what happens when we utilize this information. Let's say we have a differential equation. Say we have the differential equation y double dot minus y equals 0. And we're being tasked with solving this differential equation. Now, we wrote this on our paper. We started working on it. Our friend came by and said, hey, what are you doing that for? I solved that last year. And I found that a solution to that differential equation was e to the x. The second derivative of e to the x is e to the x. So e to the x minus e to the x does indeed equal 0. But given this information, the legitimate question is, if I'm expecting there to be a second solution, can I find that second solution? Rather than just plugging in a lot of different functions and hoping for the best, let's see what we can find. So let's suppose that y is equal to some function u times y1. The direct consequence of that then is the derivative of y is u times the derivative of y1 plus the derivative of u times y1. And the second derivative of y is u y1 double dot plus u y1 dot dot plus u y1 dot dot plus u double dot y1. Plugging this into our differential equation, the second derivative was u y1 double dot plus u dot y1 dot. I'm going to go ahead and rewrite that as two of those. 2u1, no, u dot y1 dot plus u double dot y1 minus uy1 equals 0. Grouping the terms here so that we get u double dot y1 plus 2 u dot y dot plus uy1 double dot minus uy1 equals 0. Now what you'll notice here is this second part here, I can factor out the u, which gives me uy1 double dot minus y1 equals 0. But y1 double dot minus y1 was equal to 0 by our supposition. So this is always true regardless of what u is. So this is always going to be 0. That means it must be true that u double dot y1 plus 2u dot y dot must equal 0. Now recall, we know what y1 is. Y1 is e to the x. And that means I also know what the derivative of that is. This means y1 dot is e to the x. So I can plug this in here and I get e to the x times u double dot plus 2u dot equals 0. And this is notably different from our original differential equation. First, let's observe e to the x is never 0 unless x it's, well, yeah, e to the x is never 0. So that must mean for this equation to be true, it must be true that u double dot plus 2u dot is equal to 0. Well, let's just arbitrarily make a new variable, call it w. Let w be equal to u dot, which means that u double dot is equal to w dot, and this differential equation becomes w dot plus 2w equals 0. And now we have a first order differential equation with constant coefficients, which is homogeneous. We have a couple different approaches to solve this. This is separable, or we could use integrating factor. And when we're done here, we get that w is equal to some constant e to the negative 2x. But that's what w is. Our supposition was that w was equal to u dot, so u dot is equal to some constant e to the negative 2x. Let's call this C1. Now this is another first order differential equation. This is in fact already separated. I can just integrate both sides to get that u here is equal to negative 1/2 C1 e to the negative 2x plus C2. But remember what u was. Our supposition here was that y is equal to u times y1. Y1 was e to the x. So y then, let's call this y2. Now we can just keep it as y. So y then is u negative 1/2 c1 e to the negative 2x plus c2 times y1, which was e to the x. I'm running out of room on this page, so let's flip it over and continue this consider. So what we started with, let's recap real quick. What we started with was the differential equation y double dot minus y equals 0. And somebody told us e to the x is a solution to this differential equation. Letting y then be equal to some function u times y1 because of linear independence gave us then that y double dot was equal to u y1 double dot plus 2 u dot y1 dot plus u double dot y1. And this gave us then the y double dot minus y was equal to e to the x times u double dot plus 2 u dot equals 0, letting w be equal to u dot gave us that w was equal to some constant e to the negative 2x. We're just recapping here. And then u was equal to negative 1/2 c1 e to the negative 2x plus c2. But our original thought was that y here was equal to u times y, which can be simplified to be y is equal to negative c3 e to the negative x plus c2 e to the x. And what you'll observe is, based on the information that e to the x was one solution, we got now two solutions. We got e to the negative x solves the homogeneous differential equation, and we got e to the x solves the homogeneous differential equation. And so the linear combination of those also solve the differential equation. Now, you might want to verify for yourself that these two functions, e to the negative x and e to the x, are indeed linearly independent. We can check them. Remember, by using the Wronskian, which is the determinant of e to the negative x, e to the x, negative e to the negative x, e to the x. And this is e to the negative x times e to the x is equal to 1. And negative e to the negative x times e to the x is negative 1, which is equal to 2, which is notably not 0. So these are indeed linear independent solutions. So this is fairly powerful in that if we're given one solution to a differential equation, we can find another solution. So let's do an example. Let's use the knowledge that we have one solution to find a second solution. Say we have the differential equation y double dot minus 3y dot plus 2y is equal to 5e to the 3x. And perhaps not through inspection, perhaps not because somebody came and told us, but probably maybe we just looked at this based on our previous experience and tried to solve this. We started looking at, well, what do we know about this? And then we thought, well, if we were looking at the homogeneous equation here, y double dot minus 3y dot plus 2y equals 0, that has solution y equals z to the x. Maybe we can use that to help us out. Now, this is not a homogeneous differential equation to start with, but if it were homogeneous, I would be able to say that y equals z to the x is a solution to that differential equation. So maybe we can take that information and then find a solution to the original differential equation. So again, we will begin by supposing that y equals we'll call that y1, y equals u times y1, which means that the derivative of y is u y1 dot plus u dot y1, and the second derivative of y is u y1 double dot plus 2 u1 dot or u dot y1 dot plus u double dot y1. So now plugging this information back into our differential equation, we had the second derivative, which was u y1 double dot plus 2 u y1 dot plus u double dot y1 minus 3 times y dot, which was u y1 dot plus u dot y1. Plus 2y, which was uy1. And all of that together should be equal to 5e to the 3x. y1 is e to the x, which means I can plug that at the derivative of y1, that is y1 dot, is also e to the x. The second derivative of y1 is also e to the x. I can plug all of that in here to clean this up a little bit. This is e to the x times u plus 2u. That would be a u dot. Okay. U plus 2u dot plus u double dot minus 3u minus 3u dot plus 2u, and all of that is still 5e to the 3x. Dividing both sides by e to the x and combining like terms here. Let's see, I've got a u double dot. I only have one of those. Now looking at the u dots, I have 2u dot minus 3u dot, which is negative u dot. And I have a u minus 3u, which is negative 2u plus 2u. That goes away. And dividing both sides by e to the x gives me 5e to the 2x. You'll notice we now have a second order differential equation, which is inhomogeneous. but there's no u in here. There's only u dot. Since there's no u in here, we're going to use the same trick we used in our exploration before, where I let w be equal to u dot, which means that w dot is equal to u double dot. And I can rewrite this as a first order differential equation. W dot minus w is equal to 5e to the 2x. I can use integrating factor here. The left side is the derivative. If I multiply everything by e to the negative x, the left side becomes the derivative of e to the negative x w, and that's equal to 5e to the x. Let's double check this. The derivative of this first times the derivative of the second, e to the negative x w dot. Second times the derivative of the first, which is negative e to the negative x w. Okay, we're good. And now I'm going to integrate both sides with respect to x. And get the w is equal to e to the x times the antiderivative of 5e to the x dx. Antiderivative of e to the x is e to the x. So this is 5e to the 2x plus c e to the x. But that's w. W is equal to u dot. Now taking the antiderivative of both sides to get u. This is 5 halves e to the 2x plus c e to the x. Plus a new constant. All right, let's start throwing in constants, naming them. But remember, that's u. We began with the assumption that y was equal to u times y1. y1 was e to the x. So y then, which is u times e to the x, is 5 halves e to the 2x plus c1 e to the x plus c2 times e to the x. And so we get y is 5 halves e to the 3x plus c1 e to the 2x plus c2 e to the x. So using just the observation that this solves the homogeneous version of this differential equation, just using that observation, we were able to use a substitution, assuming linear independence, we were able to use a substitution and find the solution to the inhomogeneous differential equation. This is called a reduction of order. We used one solution to turn the second order differential equation into a first order differential equation, thus reduction of order. All right, I will see you next time where we will talk about section 4.3.